Hi. So today, me and my team will be presenting our problem-based learning project for the course Algebra and Calculus DAT 11203. So before we start, I would like to introduce myself. My name is Angel Ashwini Balan from Section 1, and currently in Group 19 for this project. So to begin, our presentation focuses on the application of differentiation in real-life situations, specifically in vehicle motions and cooling fin efficiency. So through this project, we will show how differentiations can be used to determine velocity, acceleration, fuel consumption, and the optimal heat transfer rate in engineering systems. So firstly, we will explain the background of the problems given. Then we will present the mathematical solutions and the digital graphs obtained from our calculations. Lastly, we will discuss the interpretation of the results and conclude the importance of differentiation in solving practical engineering and energy optimization problem. So we really hope our presentation will help everyone to understand how calculus can be applied in real world situations. Thank you.
Question 4. A car travels along a straight road and its distance from the starting point in km after 30 hours is given by st equals to 10t squared minus 0.5t to the power of 3. A. Find the velocity and acceleration of the car after 2 hours. So, given that the car's distance after 3 hours is st equals to 10t squared minus 0.5t to the power of 3. So to find the velocity, we need to differentiate this. So Vt equals to s prime t. So the answer is 20t minus 1.5t squared. And then it says that the velocity of the car after 2 hours. So when t equals to 2, we need to replace the value 2. V2 equals to 22 minus 1.5 to square. And then we got the answer is 34 km per hours. This is for the velocity, but for the acceleration, we need to do the same thing, which is we need to differentiate using the derivative of Vt. So, At equals to V prime t. So, 20 minus 3t. And then we also need to replace the value 2. 20 equals to 2, A2 equals to 20 minus 3, 2. So we got the answer is 14 km per hours. So now we can see that the cars is moving at 34 km per hours and accelerating at 14 km per hours after 2 hours. The question read, determine the rate of change of fuel consumption if the fuel used in a liter is proportional to the velocity of the car. If the fuel consumption rate RT in liter per hour is proportional to the velocity, so that RT equals to kVt, take K equals to 0.05 liter per km. So, given that the car consumption rate is RT equals to kVt, whereas K is equal to 0.05. So we just need to replace the value of K. So K 0.05, and then Vt so Vt is 20t minus 1.5 t squared. So we got the answer is t minus 0.075 t. And then rate of change mean r prime t. So we need to differentiate this. So dr over dt equals to 1 minus 0.075 0.50. So this is the final answer.
Hi everyone, my name is Christina. I will explain question 4.1c, which is a graph of velocity against time. The velocity question is Vt equal 20t minus 1.5t. Based on the graph, we can see that the graph form a downward opening parabola. At the beginning, the velocity increases as the time increases. These show that the car is accelerating. The graph then reached its maximum point at approximately 66.67. This means the car achieved its maximum velocity of about 66.67 km per hour at 6.67 hours. After reaching the maximum point, the graph starts to decrease. This indicates of the velocity decreases over time and the car begins to decelerate. In conclusion, the motion of the car shows that it's accelerating first before slowing down after reaching the maximum velocity. That's all for me. Thank you.
Hi, my name is Angel Ashini Balan and I'm from Section 1 and Group 19. And today I'll be explaining question 4.2a, which is about cooling fin efficiency. So the heat transfer equation for this is Q of x equals to 120 times e to the power of negative 0.1 x. So in this equation, x represents the fin length in centimeters. The objective of this question is to find the optimal fin length that gives the maximum heat dissipation. So firstly, we have to differentiate the function using the product rule because the equation contains two functions multiplied together. And after differentiation, we will get q prime of x equals to 120e to the power of negative 0.1x multiplied by bracket 1 minus 0.1 x bracket. Next, we have to find the maximum point. So we let the derivative equal to 0, which is 120e to the power of negative 0.1x bracket 1 minus 0.1x bracket equals to 0. So since the exponential function cannot equal to 0, we solve it by doing 1 minus 0.1x equals to 0, and then 0.1x equals to 1, and lastly x equals to 10. So the optimal fin length is 10 centimeters, and after that we substitute x into 10 into the original equation to find the maximum heat transfer rate, which is q of 10 equals to 120 times 10 times e to the power of negative 1, which is approximately 441.46. So therefore, the maximum heat dissipation is approximately 441.46 units. In conclusion, the cooling fin works most efficiently when the fin length is 10 centimeters because it produces the highest heat transfer rate. So that is all from me. Thank you.
Assalamualaikum and hello everyone. My name is Ayra Tasha binti Abu Isman. My metric number is AA251861. So for the question 4.2b, which is my part, is about plotting the graph digitally and finding the maximum point for the heat transfer function. So the equation given is Q of x equals to 120x times e to the power of negative 0.1x. So to find the maximum point, we first differentiate the equation using the product rule because this equation involves multiplication between two functions. So the product rule is dy over dx equals to u dv over dx plus v du over dx. Next, we let u equals to 120x and v equals to e power of negative 0.1x. Then we differentiate both functions. For u equals to 120x, the derivative is 120. For v equals to e power of negative 0.1x, the derivative is negative 0.1 e to the power of negative 0.1x. So after substituting into the product rule, we get dq over dx is equal to 120x of negative 0.1 e power of negative 0.1x plus e power of negative 0.1x of 120. Then we simplify the equation to dq over dx equals to e power of negative 0.1x of negative 12x plus 120. So to find the critical point, we set the derivative equal to 0. So e power of negative 0.1x of negative 12x plus 120 equals to 0. Since the exponential function can never be 0, we only solve negative 12x plus 120 equals to 0. So we get x equals 10. Next, we substitute x equals 10 into the original equation to find the maximum value. So q of 10 equals to 120 of 10 e power of negative 1 gives approximately 441.46. So the maximum point is 10, 441.46. So based on the graph that I've shown you, we can see that the heat transfer rate increases until x equals 10, then starts decreasing afterwards. So physically, this means that the optimal fin length is 10 centimeters because it gives the highest heat dissipation efficiency. If the fin becomes too long, the cooling efficiency decreases. So I think that's all from me. Thank you.